I'll update you. What we've been doing in the past couple of years. Sorry. So my field is the main research area of my interest is the 21-centimeter cosmology, which deals with emission and absorption by neutral hydrogen populating the high redshift universe here between the recombination and that of the epoch of reionization. And I'll be telling you today what we do to explore this epoch. It's an unobserved epoch yet. There are very few observations that are either questionable, they're still tentative, or upper limits, so we don't have a full picture of what is happening at those times. So this is the epoch when the very first stars formed in very small dark matter halos that were just able to form stars, usually through cooling of molecular hydrogen or atomic hydrogen. So for comparisons, these are halos about 10 to the 6, 10 to the 5 solar masses, much smaller than our own Milky Way. I will first give a broad introduction because there are many students that joined us in the past 2 years and haven't heard my talk, so bear with me if you know this field, and then I'll update you on the new results. So this is again the cartoonish evolution of the universe from the CMB, from the hydrogen recombination to the present day when we have huge galaxies and clusters of galaxies and well-developed cosmic web. But of course, the universe undergoes all the intermediate stages of its evolution from formation of first halos and stars, and then these halos grow and form the big evolved structures that we see today. But our observations are not yet grabbing all this picture because we have the beautiful CMB, cosmic microwave background data from many experiments with the latest being Planck, which Cambridge is actively participated in. And then at lower redshifts, we have observations of cosmic web galaxies with DESI and CHIME and BOSS and many other surveys. However, the surveys of low redshift universe cover only very recent past, a very small patch in cosmic history going all the way to redshift 3. And at higher redshifts, we have sparse observations, so there are no big surveys that tell us about structure formation. There are observations of bright galaxies or observations of more typical sky, but through a gravitational lens, which magnifies these images. And the most distant sources that we can see today is this galaxy at redshift 11 that is not very well resolved. ALMA sees galaxies at about redshift 10, which are very rich with elements, and also have a bunch of high redshift quasars at redshift around 7 and maybe 7.6 some. So these are really very few bright point sources that we have at the epoch of reionization, and we have nothing at redshift between the CMB and these very early structures, except for a tentative detection that by edges of the 21-centimeter line that I'll mention later in the talk. Of course, we are all waiting for JWST that was successfully launched, as we all know, and JWST will push this limit of observable galaxies to much higher redshifts. If we are lucky, out to redshift 20, that's what Roberto told me. So JWST will provide a much better picture of the high redshift universe and the process, the typical galaxies that ionize the universe. So 21-centimeter line is another promising probe of this epoch, and it will basically bridge the gap between the CMB and the epoch of reionization by measuring what's going on with neutral hydrogen. So all the regions between these gray ionized areas are populated by hydrogen atoms, neutral gas that emits the 21-centimeter photons produced in the spin flip transition by hydrogen atoms. So we will have information about all these neutral regions, hopefully in the not so far future. At the moment, these are very early days, as we only have, as I said, upper limits and one tentative detection. So one can view 21 centimeter signal as distortions on the radio background spectrum. So this is a CMB spectrum brought by a series of experiments. For example, Kobe measured the blackbody spectrum of the CMB to high precision. And so we know that it's blackbody, but actually hydrogen atoms interact with this CMB temperature, and they introduce spectral distortions in the very low frequency end of the spectrum, so even lower than what you can see on this graph. So this is a line produced at the 21 centimeter wavelength intrinsically, and when it redshifts to us, it would introduce distortions at wavelengths between from 30 megahertz to 250. So it's very low frequency signal. And the spectral distortion is non-uniform around the sky, as I will show you later, and it also has a characteristic shape with an absorption trough and then emission detail, emission part that will actually tell us what's going on at these high redshifts, and it can be used as cosmic cloak that tell us when stars form, when first population of X-ray binaries forms, and when very massive galaxies form and start ionizing the universe. So again, because it's a line, we can, and we know that its intrinsic frequency of 9.4 gigahertz, we know how it redshifts, and we can, by observing at different frequencies, we will know from which redshift the information is coming. So this is an example of an output of my simulations, what is called light cone. So here on the x-axis is cosmic time, and yellow is close to zero. So this is a recombination, CMB decoupling, and this is today the end of reionization. And as we go, the universe evolves with time in this X direction, and Y direction is just sliced through my simulation box. So you see how the 21 centimeter information here evolves with redshift, and also it especially fluctuates if you cut it at specific redshift. So there is a rich information in the signal that evolves with time and with scales, and it contains information about the sources that we can extract from the signals once they're observed. So a bit more into details, the key quantity that we can extract from the signal is its spin temperature, which is just the abundance of atoms in the excited spin flip state, as opposed to the atoms in the low state. So it's just the characteristic temperature of this transition. And it depends on various astrophysical quantities. And by measuring the signal that is in this spin temperature, the intensity of the spin temperature, we can extract several quantities. So let's go through that. So first of all, if you have just CMB and a bunch of atoms for a long time in one bath, they will come to thermal equilibrium. So this process takes spin temperature to the temperature of the radiation. So it might not be just CMB, it can be also that high redshift galaxies add radio photons to the background. So the spin temperature will measure any radio background that exists at high redshift. Then if atoms collide, if atoms have some kinetic energy, they will collide and will have some gas temperature. So these collisions drive spin temperature again to the thermal equilibrium to the temperature of the gas with some efficiency coefficient xc. So that depends on the density of these atoms. And finally, there is a very important effect called the Thousand field effect that is an atomic physics effect. So in the presence of Lan alpha radiation produced by stars, if you are in initially n equals to 1 state, which is actually, that's where the 21 centimeters produced, this level is split due to interactions between spins of proton and electron. So atom can be here and then absorb Lan alpha, re-emit Lan alpha, and end up in a different hyperfine state. So as soon as stars produce this line alpha photons, they will enable 1000 field coupling, and this will drive again the spin temperature to the cover temperature of the radiation, which is again very close to the temperature of the gas. So there is this efficiency coefficient X alpha that depends on how many line alpha photons there are here or in the intergalactic medium. And with this efficiency coefficient, the spin temperature will tend to the gas temperature again. So overall, we can write down this formula that gives us the spin temperature as a function of different astrophysical processes that are present at high redshift universe. So overall, what 21 centimeter measures is the contrast between radio background, which here I take to be the CMB, this white line, the CMB temperature redshifts and cools down. And the gas temperature with some efficiency coefficient. So gas was first coupled to the CMB by collisions, and then it decoupled, started cooling down much faster, and this contrast grew. And then at some point, X-ray sources kicked in and heated up the gas to the temperatures above the radio background. So what we can measure is this difference, but there is this efficiency coefficient that depends on the Lyman alpha photon intensity. And this intensity grows with the growth of stellar population. So the more and more stars there are there, the higher and higher this Lyman alpha background is. The Lyman alpha coupling is usually very quick. So as soon as there is enough photons, there is a fully coupled 21 centimeter transition to the gas temperature. And then, of course, we have the reionization history. So reionization in principle starts with the formation of the first stars that produce UV photons and start carving out ionized regions in the overall neutral gas. But then this process is very slow and it takes a lot of energy. So at very high redshifts, we don't see it we don't see its effect on the large scale 21 centimeter signal. So this neutral fraction is close to 1 at high redshifts, and then when very massive galaxies that are more efficient in producing ionizing photons build up, this fraction of gas that is in neutral state drops quickly, and the reionization is complete. So the 21, of course, the temperature of the gas and also Lyman alpha intensity and ionization will be especially varying. So we will have this curve, the yellow one, fluctuating around the sky, depending on where you are in the universe. And at 21 centimeter from that location, we'll measure the contrast between the radio temperature and the properties of the universe at that point. So that's just to say that every star forming region produces different types of radiation. In the Lyman alpha band, it can produce radio photons, X-ray photons, and these photons are emitted from the star forming region, and they all have some efficient horizon, so they propagate to characteristic distances. And for example, X-rays can output their energy a few hundred megaparsecs away from the source, depending on the energy actually. So this will create non-uniform structure in the 21 centimeter signal that we can study also. So that's why we have this rich structure of fluctuations and general evolution as a function of time. And we can look at the monopole, so just averaging over this y direction here and looking at how the average signal evolves, and that's what we usually see. There is this big, deep absorption trough created by stars. So Lyman alpha coupling happens. These photons couple spin temperature to the temperature of the gas, which was colder than the radiation. So we see it in absorption. The X-rays kick in, start heating up the gas, and then reionization happens, and the signal drops to 0. So that's the mean evolution, and the signal was recently reported in 2019, claiming to detect this absorption profile from redshift 18. So we will talk about it in a few two minutes or so. And we can also study the structure of fluctuation. So like with the CMB, we can produce power spectra. So it's just Fourier transform of this CMB map. And with 21 centimeter, we would have three-dimensional information. So we have two-dimensional slice, but at every redshift separately. So we can track, for example, how fixed co-moving angular scale, power on that scale evolves with redshift. And this would have also information about non-uniformity of 21 centimeter signal introduced by different sources. For example, from very high redshifts, we would measure how Lyman alpha sources fluctuate around the sky. Then when X-ray sources dominate, we would measure fluctuations in 21 centimeter due to the gas temperature fluctuations. And then finally, the ionized bubbles will introduce will boost the signal. So again, by studying how this evolves with redshift, we can understand how the universe progresses. So there are many telescopes that are trying to observe the signal in both global signals, so sky average spectrum, and the fluctuations. These are interferometers. The SK is a big international project that is just starting, while others are taking data. For example, LOFAR and WLIDA and HERA have been taking data, publishing upper limits. NANUFAR has already also taken data, and these global signals reach is the effort here in Cambridge and South Africa that is with the first antenna deployed just in March, so now a few weeks ago, and SARA-3 I will also mention in a second. So just to have us all on the same page, so the first detection ever of 21 centimeter signal from high redshifts was published in 2019 from the EDGES collaboration. This is an antenna located in Australia. And they reported that they see a cosmic signal from redshift 18 here. So that would be the first ever signature of the first stars, right? So by seeing this absorption profile, if it's cosmological, then one would have information about the onset of star formation, production of Lyman alpha photons, and X-ray heating. So if it is cosmological, then stars would have to form at redshift 20, and first X-ray binaries at redshift 16. So that sits well with our astrophysical picture. However, the absorption trough was so deep that it's inconsistent with standard models that assume the background radiation is the CMB. So these are gray models here, and the detected signal is much deeper. So that's why the community is rather skeptical about its cosmological origin. There are attempts to explain it. For example, if one adds radio background to the CMB, then this contrast deepens and the signal can be then explained. Or if gas is colder, so we again deepen this contrast from the other side, and we get this absorption. So many experimental teams try to verify this detection and see if it's real or not. I'll briefly tell you about the status. So the most interesting one is SARA-3 that was published just I think a few days ago, actually, or a week ago in Nature Astronomy. And this is a small antenna located on the lake to avoid to avoid the reflections from the ground. And they actually don't see the EDGES signal. So they took data and they tried to fit the best fit EDGES profile to their data, and they rejected at 95.3%. So that's great, but it's still very weak rejection. So we don't know if it's there or not. And so this is a big deal in the field now. Right, so we'll give EDGES still a benefit of doubt until there is stronger verification. On the reach side, so I mentioned the antenna has just been placed in the Karoo Desert in South Africa, and that's Eloy here. He's a PI from the Cambridge side, and Dirk is a PI in South Africa. And few people from Cambridge went to help to actually deploy the antenna with a very nice rainbows there. So hopefully, as soon as it's ready and plugged in, we will start seeing the signal. So if you're interested to know more, you can visit the webpage, and we will have actually a Kavli workshop on 21 centimeter signal, where you can hear talks on Reach in April 11th to 13th. Okay, as I mentioned, so this is the edges detection, and we can try to build models to explain it. So for example, adding radio background to the model that I showed you would create signals compatible with edges. And such model would also predict power spectra. So we would also have enhanced power spectra compared to the ones expected in models with the CMB as a background radiation. And that's a testable prediction. So one can go with an interferometer and try to find this power spectra or not, and rule out the edges compatible models. So there are experiments that are already looking at that redshift range. For example, LOFAR has a dedicated program called ACE to look just at high redshifts and try to see if there is a signature or not. But the limits are still too high. These are our predicted astrophysical scenarios with boosted radio background, and LOFAR limits are still too high to say anything about this experiment, about edges. Other upper limits is a quote from Irena that Irena compiled. So other upper limits are at lower redshifts than what can probe edges, so they cannot directly tell us whether or not edges is a true cosmological signal. And they are also still a bit too weak to probe cosmological 21 centimeter models with the CMB as a background radiation. For example, Hera is our best upper limit that exists at the moment. However, this upper limit can already tell us something about this extreme radio background models, and I'll show you results later in the talk. So this is just to say that Hera and edges are looking at different redshift regimes. So models that are compatible with edges would be already saturated by Hera redshift range, so which is around redshift 8, much lower than 18. And so Hera is not sensitive to these models because in the edges scenarios, star formation happens earlier on. So we said stars start forming at redshift 20, X-rays at redshift 16. And so by redshift 8 or 10, the signal is expected to be smaller, while Hera is sensitive more to models which have most of the action happening later. For example, the galaxies picking up at redshift around 8, and the power spectra are stronger there, so we can rule them out. So there are also many plans for space missions to explore 21 centimeter from space. There are several advantages to that. First, we will avoid ionosphere, which blocks very low radio frequencies. And because of ionosphere, I cannot actually probe signals from dark ages from redshift 30 and above. So to do that, we need to go to space. In space, we would also avoid radio frequency interference, such as created by any laptops or antenna on Earth. And so we would have access to dark ages. So there are many actually groups around the world that are planning their space experiments from a chain of satellites orbiting around the moon to a big satellite system in space, to lunar landers that would just spread the mesh of radio detectors and interferometer. So that's the future. So let's now talk a bit more about what can we learn if we detect the signal. I already hinted about processes, for example, Lam alpha coupling, heating, ionization, but there are actually more subtle processes that can be constrained or that need to be taken into account to make reliable predictions for the 21 centimeter signal. And one important thing to realize is that the signal is sensitive to the integrated effects. So, for example, gas temperature doesn't jump suddenly. We need to solve equations and integrate around the whole redshift range of thermal history to know what the gas temperature is at every redshift separately. And the same for Lyman alpha photons. Reionization is a bit more, can happen on shorter time scales. So 21 centimeter would track the whole history of these events. And therefore we need to build simulations that evolve these quantities from very early on, from initial conditions to the later stages. So there are, as I mentioned, several subtle processes that we need to be aware of. For example, I'll show you the results of what is called Lyman alpha heating. And this is heating by Lyman alpha photons when they recoil, when they scatter from atoms, and atoms get some of their energy. So this heating was actually neglected until, well, it was mentioned in several papers, but no one took it into account when producing constraints with 21 centimeter upper limits. We were used to look at models of this gray type, so these are global signals versus power spectrum. And these gray models have conventional heating mechanisms such as cooling. The gas cools down with the expansion of the universe, and then it heats up by X-ray photons. And in this case, gas can be very cold. And also there is what is called a adiabatic cooling limit. So when the universe doesn't have X-ray sources and the temperature just drops with the expansion of the universe. So that's the coldest scenario that you can get. And if stars form in this scenario and produce a lot of Lyman alpha photons, they would couple the gas to this cold couple the 21 centimeter line to this very cold temperature, creating these deep absorption profiles. However, if one includes a very subtle effect of Lyman alpha photons that I'll explain in a second, we have this completely different picture. So we need to take that into account. So back to Lyman alpha photons, they couple the spin temperature to the gas temperature, and again they enable this absorption of the 21 centimeter line. And this is when Lyman alpha photon is absorbed, the atom jumps to 2p level, and then Lyman alpha is re-emitted, and the atom can end up in the different hyperfine state. So this effect is well understood, and we always take into account. And adjusting star formation process. So for example, there are feedbacks to star formation. It can be more or less efficient in small halos that would just shift 21 centimeter to absorption to higher or lower redshifts. So that's all good. However, it was realized that Lyman alpha photons by scattering can pass some of their energy to the gas. And there are two types of photons that can contribute to this process. First are those emitted between Lyman beta and Lyman alpha line. So they would just redshift until they reach Lyman alpha line. And these are so-called continuum photons. They would contribute to heating up the gas because they have slightly higher energy always. So they would pass this excess energy to the gas. And this process alone can heat the gas up to 100 Kelvin. So that's significant. And another type of photons are injected photons. So if there are photons produced between Lyman beta and Lyman limit, so it's higher energies, if they redshift, they can enter into the higher energy states of hydrogen and then cascade down until they reach Lyman alpha line. So these photons can actually, because they're injected into the line center, they can both heat and cool the gas. So green part here is what goes into the heating. So sorry, this is a line profile around Lyman alpha for continuum and injected photons. So the photons that are a bit redder will contribute to heating. So blue to heating and redder to cooling. So this orange is cooling. So for the injected photons, heating and cooling almost balance each other out. So in net, they contribute very little, and overall we have heating from this continuum photons. However, this is a temperature-dependent effect. If the gas is very hot, it actually turns out that the effect of continuum photons becomes relatively negligible, while the injected photons still contribute. So we can get scenarios in which gas is cooled by Lyman alpha. And similar, there is an effect called CMB heating. It was introduced only in 2019, very recently, and not many people take it into account in the simulations. But it can heat up the gas. There is exchange of energy between, because the 21 centimeter levels a couple basically radio background, gas temperature, and their own spin temperature. So there is exchange between all this thermal baths. And so the energy from the CMB can actually go in, or any radio background can go into the kinetic temperature of the gas. So if there are no other heating mechanisms that can contribute. So we looked into how these effects actually affect the temperature of the gas, and this is a heating rate. For comparison, we have a Hubble heating or cooling rate from Hubble. Expansion of the universe is a function of redshift. And then this blue line, light blue line, is heating by continuum photons from line alpha, assuming that there are no X-ray photons to heat up the gas. So at redshifts around 15 in this model, gas starts to be heated up by line alpha. And the CMB heating, it's smaller than the Hubble expansion cooling, but it still can be important. And the injected photons are first contributing very little, but then they catch up. And so they annul the effect of this heating process. So here you can see how gas temperature actually depends on presence of this line alpha heating process. So in the absence of any heating just with the CMB cooling, we have this dot dashed line. But if we add either CMB heating or line alpha heating, the temperature completely changes. So we will see that in the 21 centimeter signals, especially at low redshifts. And at low redshifts is because we do need to accumulate enough line alpha photons in the background to heat up the gas, right? So we see that without the line alpha heating effect, and with this line, so this is without and this is with, the signals drop almost by 2 orders of magnitude just by including this subtle heating effect. And the absorption of the global signal becomes also much shallower with this heating. So this actually has important implications on the upper limits that we derive today with telescopes, because at the moment, we can only constrain these very deep absorption profiles that are obtained in the coolest scenarios. So we do need to be careful with including all the heating components. And when you study the different astrophysical scenarios, for example, if stars are efficient or not, if stars form in small halos or not, you get this blue range of models, which is much shallower than previously was obtained with this models that ignore heating scenario, line alpha heating. Another effect that is subtle, but that is often neglected, is that line alpha actually scatter, and it sounds trivial, right? Because line alpha absorbed and then immediately emitted, and another atom absorbs them until they redshift out of line alpha line. These photons. So when we calculate line alpha coupling process, we do need to take the scattering into account, which is not usually done. Usually people assume that line alpha just propagate, and then at some point it creates this sort of scalar field coupling of 21 centimeter line, and it all happens at some effective radius. But actually, in reality, it all has a distribution. So you see here on the top panel, the distribution of the scattering. So distances at which photons couple the gas to the spin flip transition. And so there is some, we do need to take into account all these scatterings. So this process would affect the fluctuations in the 21 centimeter signal, although it's relatively weak, but it's interesting. So on the top panel, you see on the left, the case when we don't take into account the scatterings, and then on the right is with scatterings. So there is an effect on the fluctuations of maybe 50% or 20%. And this is mainly high redshift effect. So it's important everywhere where there are line alpha photons. So if we have no X-rays to heat up the gas and heating happens due to line alpha photons, we will see difference between scattering, with scattering and without scattering throughout the redshift evolution. But if we do it some X-ray physics, then the effect only happens at high redshifts. And so when we take all this line alpha physics into account properly, we get line alpha coupled bubbles in the universe at early times. So here we see that every galaxy would create big observable bubbles at redshifts around 20 that can be observed directly with a square kilometer array. Sorry. So now there are several other interesting processes, and one is explored by our student Thomas Gacy-Jones. He's at physics and jointly co-supervised with IoA and Will. And so what Thomas did is to explore how initial mass function of the first population of stars, population 3, which are metal-free stars produced out of primordial gas, predominantly hydrogen. So we don't have any constraints on their initial mass function. It can be either very top-heavy or bottom-heavy, so that these stars can be very massive or less massive. So we just don't know. And we looked at how properties of the stars would be seen in the 21 centimeter signal from cosmic dawn, and if we can constrain this initial mass function with 21 centimeter in the future. So Thomas did a great job by taking several codes and just on his own, running them and looking at the evolution of stars with MESA, and then evolved stellar atmospheres with CLASTI. And then he compiled spectral energy distribution of these first stars as a function of stellar mass. Then he calculated the emissivity of photons per baryon for a star of different masses. So this is the total emissivity, how many photons in the line alpha band each star produces as a function of the mass of this star. So it turns out that there is a peak around a few solar masses. So these stars are the most efficient in producing line alpha, and then they become less efficient due to their properties, and they're also less lived. If the star is more massive, it's shorter lived. And so there is a kind of plateau. So for stars between 20 and a few hundred solar masses, their emissivity doesn't depend on the stellar mass. So then that's what he found for 21 centimeter signal. This is the power spectrum as a function of redshift again, and we see that for there is difference in the signal when we are talking about smaller masses. So this purple range, the signal depends on the stellar mass, and that's the case if we take all stars to be at this mass. So for example, 2.5 solar masses, we would get this type of signal. 10 masses, we would get this. But then there is, because of this plateau, there is no sensitivity to stars above 20 solar masses. So all stars from 20 to 500 would produce the same identical 21 centimeter signal in this yellow band. And so we will not be able to distinguish between initial mass function that is only composed of, say, stars of 500 solar masses or of stars of 60 solar masses. And then he also looked at the spectra within the Lyman band, which is very important for the 21 centimeter signal, and produced final predictions. So how the signal depends on the full initial mass function if you take the whole distribution. So considering very extreme scenarios from self-Dieter-like. So very dominated by small stars, or something flatter and dominated by heavier stars. So this shows that 21 centimeter again can be sensitive to stars of smaller masses. It can tell us whether the initial mass function was dominated by small stars or heavy stars, but beyond a certain limit, it will not tell us it will not be able to tell us if it's completely top heavy or within the few tenths of solar masses. I'll skip this. So another important component is the X-ray physics, because gas is heated up by X-rays, and I talked about it here several times, but just to mention it for completeness. So the property of X-ray sources, both their spectral energy distribution and intensity is important and drives this heating scenario. And the peak in 21 centimeter signal from the distribution of X-ray sources can be either at very low redshifts or very high redshifts. So it's very uncertain, and therefore we'll need observations to constrain it. So just schematically, if we have very soft X-ray sources, which output photons of just below 1 keV, most of their energy will be injected close to the source, and it will lead to very strong fluctuations in 21 centimeter signal, while hard X-rays would be more diffused and heat up on gas on much larger scales, contributing to smaller fluctuations. And my postdoc Nina is also doing a great job. She's calculating the spectral energy distribution for population-free binaries. So they are completely zero metallicities forming from pristine gas. And she evolves them with redshift, calculating the X-ray spectra also for different initial mass functions. So here you see preliminary plot shown for also top heavy or bottom heavy mass functions in the intermediate case. And we see that there is quite a bit of difference between these IMFs in terms of X-rays. So when we add this X-rays to what Thomas has done, we expect to see much stronger difference between heavier IMFs in the 21 centimeter signal. So Nina is here. And so if you have any questions about that, please talk to us. I don't go into details here because just in the interest of time. So another interesting process is that high redshift galaxies can also produce radio. For example, if there is a black hole and there is a synchrotron radiation produced by particles in the magnetic field of the galaxy, then we would create radio emission, and adding this radio emission to radio background that will increase contrast between the gas temperature and the radio, and thus increasing the 21 centimeter signal. But if this radio is produced within galaxies, then it will also fluctuate on the scales of the galaxies, and that will increase fluctuation pattern in the 21 centimeter signal. So we explored this model as well. And it turns out that even for modest galaxies, so not completely like today, but a bit stronger, which is maybe exotic, but such signals would create stronger 21 centimeter predictions, which can be constrained easier than models without these radio galaxies. So I already showed this plot. So in the extreme cases, we would create edges-like signals, but in the more normal cases, we would create slight enhancement about the predictions in the case of the CMB on the radio background. And so Stefan also did a great job. I cannot say that just one student did a great job. So Stefan took this enhanced radio background models and looked into how they are constrained with Hera, because in this case, we expect stronger signals than the CMB on the case. So this black line here marks the limit in which the CMB radio background. So that's an amplitude of models, maximal amplitude of models in the case when the background is CMB. If we add extra radio background, it just jumps these models up. So many of them are actually above Hera data, this green lines, green dots. And so Stefan studied how what models are excluded and what can we say about actually astrophysics using these limits. So he wrote the whole code and did the parameter estimation. So it's in parameters of the simulation, but the key idea is that the parameter that regulates radio background is radio production efficiency that is relatively to the galaxies today. So 1 in these units of FR is equivalent to radio galaxies today. And also X-ray production efficiency here, again, normalized to the present day universe, can be constrained already with HERA data quite neatly. So HERA would exclude models that have high power spectrum. To produce such, we need both strong radio, so we need this high contrast that is reached when the radio background is high and gas temperature is low. So models with low X-ray heating efficiency and high radio are excluded. And this plot shows prior versus posterior in the radiation temperature versus gas kinetic temperature. So these are normal human readable units. So HERA excludes all this range of very strong radio background and also relatively low gas temperatures. And then we looked at how HERA constraints compare to other information that we can have on this high redshift universe. For example, we know that Chandra X-ray satellite observes there is a portion of X-ray radio background that is unresolved, so it's not characterized. We don't know where it's coming from, and it can be used as an upper limit on this high redshift X-ray population, right? So high redshift X-ray sources cannot over predict this limit of seen by Chandra. And so this would create models with very high values of this X-ray parameter that are excluded by Chandra, so these crosses are not compatible. On the other hand, there are surveys that only probe radio background. For example, ARCADE and the LWA telescopes have a measurement of radio background intensity. And also some of these models over-predicted, so we can rule them out by using the ARCADE data. And so it turns out that HERA limits are complementary, so these models are allowed by LWA and Chandra, but they're color-coded with HERA likelihood, so some of them are excluded, are ruled out by HERA. So HERA is complementary to both radio surveys and X-ray surveys. And then Harry also did a great job, really. He took all the models and he took the data from SARAS-2, so which is a global signal experiment, which we got hands-on, and looked at what models are compatible or not compatible with SARAS data. So SARAS is the same team that recently rejected edges at 95.3%, and SARAS-2 is their lower redshift experiment. So SARAS-2 is less sensitive, and it does rule out models with very deep absorption. So this blue are models in our prior set that are incompatible with SARAS, and red are those that are still compatible. So we do see that there is sensitivity to models with deep absorption, but in terms of astrophysics, all these probabilities are quite flat, so we cannot we cannot exclude any parameters separately. There are combinations of parameters that lead to these very deep absorptions that are excluded. And so now we are looking at SARAS-3 data, actually, that is at the higher redshift regime here, and stay tuned about these results. Okay, and we are also interested in looking at what different dark matter models can do to 21 centimeter signals. So, of course, dark matter would, Tibor is doing fantastic job, right? I'm sorry. So he's running hydrodynamical simulations with different dark matter models with the aim to produce a framework where we can vary dark matter scenarios, compute 21 centimeter signals, and then see if they're compatible with data or not, and try to constrain the nature of dark matter. And dark matter is the basis of everything, so it regulates how many dark matter halos, so star-forming regions, are produced eventually. So, for example, we are now looking at what is called fuzzy dark matter, where dark matter is in form of axions that can have very low masses, and their de Broglie wavelengths can be of few kiloparsecs. So in this case, there is suppression of structures, and it can result in less stars formed or less star forming region, but it can also lead to star formation in filaments. And so what we need to do here is to characterize the abundance of filaments. So Tibor is looking at the Nexus algorithm, which can separate the filamentary network from the cosmic web, for example, and then look at the abundance of filaments and their properties, and then look at which ones form stars or not, and make predictions for these models. And for example, now we looked at triaxiality of halos in these fuzzy dark matter models, which predict more dense filaments, and then halos are expected to be also more prolate compared to the CDM case. And these are all preliminary results still, but they're very interesting. Okay, and I'll stop here with my conclusions. So I showed you that JWST will be great when we have the data on the galaxies themselves, but 21 centimeter signal is a complementary probe. It probes everything except for galaxies, so it probes the properties of intergalactic medium and the effects of galaxies on intergalactic medium. And I showed you that we do need to take subtle effects such as laminar overheating and initial mass function of stars into account when we make realistic predictions for the signals. And also there are current experiments that are producing upper limits that can be used already to constrain these first populations of stars and black holes. Thank you very much for attention.
Yeah, let's start.